Hi, everyone. It's my pleasure to introduce Daniil Tiapkin today. He is currently a PhD student at Ecole at the University in Paris, Ecole Polytechnique. And today he is going to talk about optimistic exploration in reinforcement learning without bonuses. So welcome, Daniil, and yeah, please go ahead.
Yeah, thank you very much for introduction. So this work was done with this very large collaboration with all these people that you can see on this first slide. So, and I will move to things that going on. So first thing that so I will talk about array. It is very easy deducible from the topic of the talk. I will just a little bit skip the slide and move to the actual thing that we are doing. So the question that we are trying to answer is this very open question with a lot of answers and a lot of things. Is that how to do provably efficient exploration and exploitation in array? So this challenge is very difficult because of very simple reason. Because exploration and exploitation are just contradictory goals, and we need somehow interpolate between them and somehow do it efficiently. And by efficiency, I also mean that all these algorithms in perfect world, in ideal situations, should be generalizable from the simple theoretical settings that we can actually prove a lot of things to practical setting of deep reinforcement learning, then we solve in Atari games or anything like that. So, and in my talk, we will talk about also how to generalize our algorithms to deep array setting. So yes, short summary of everything that will go afterwards. So for people familiar with bandits, it will be very easy to understand what's going on. First, we'll start from introducing some algorithms based on posterior sampling or things related to it. Generalize base UCB to array setting with nearly minimax optimal guarantees, and also develop some computation efficient version of posterior sampling algorithm, and also provide some deep array implementation of the first algorithm. And in the center of all these algorithms will be some purely probabilistic sujet about Dirichlet distribution and how to compute tails of the weighted sum of Dirichlet distribution, or estimated. So first, let's familiarize a little bit with notation. I will consider just finite horizon episodic tabular small MDPs with finite horizon, finite number of standard actions. Learning process is as usual in finite horizon setting. We have episodes. For each episode, we staying as state STH, taking action ATH. Afterwards, next state generates from policy that depends on the state, on the step, and also output rewards that we, for simplicity, will assume that known and bounded. And for all this thing, we can compute value that will be expected rewards starting from step H, starting at state S. So we can define value for any policy, and if we optimize this thing for all policies, we end up with optimal Bellman equations that defined as described here. So we compute Q value that is this way. Afterwards, update V star as max over Q values, and it will show us how to act optimally, because optimal policy will be always assign mass only on argmax of Q star fixed S and for any S. But as typically happens, okay, we cannot do it because we don't know our transition kernel. And to somehow understand how to work in this situation, there was developed setup of online array. In this case, we interact for capital T episodes, not K, T, capital T episodes, each of length H. So this, and we just interact with environment for capital H steps, and afterwards we start again from initial states that can be either obviously adversarial, so chosen a sequence and prior of all computations. It can, but we will assume that it's fixed because it's very close scenarios anyway. And our goal is to minimize regret at the sum of suboptimality gaps of each policy. So before talking about our algorithms, let's just take a little bit on what was known before. So one of the most classical, I would say, way to address unknown pi hat is to not just use maximum likelihood estimate of it, but also we need to drive somehow exploration, for example, using exploration bonuses. And we will have in all this thing, p hat v plus bonus, it will be upper approximation of pH v star. So that's the core idea, and this upper approximation helps us a lot with analysis. It allows to reduce analysis to more, I would say, classical statistical things. And with proper choice of bonuses that should somehow track variance of our estimates and etc. We have nearly minimax optimal regret bound up to second order term, maybe if it's no use of any doubling trick, as known for a moment, and with some logarithmic terms that seem to be okay, so we don't care too much about logarithms. But this algorithm has its own contrasts. For example, it have not so good empirical performance even on tabular experiments, and it's difficult to scale to deeper setting because these bonuses are very highly related to number of visits to state action pair, and it's non-trivial how to extend this notion to deeper setting. It's possible somehow, but rather non-trivial. Alternative to this approach, let's use another type of bandit algorithm at the line of it. So let's do posterior sampling. For posterior sampling, we just replace our unknown p in optimal Riemann equation by sample from posterior distribution. And we end up with some noisy approximation of our pH v star h plus 1, or in this case, pH v tilde. And basically, the problem with exactly this algorithm, as I described here, that it's extremely hard to analyze. And for a moment, up to my knowledge, there exists analysis only in the case of Bayesian regret. Then we have some prior knowledge about our model. So without in minimax setting, then we try to be optimal with respect to any model. Analysis still not exist for such a type of algorithm. But in practice, it works pretty well. So, and also it can be in spirit generalized to deeper setting, as what's shown by Bootstrap-Duquesne algorithm, for example. So to make something about this algorithm in more concrete way, let's just understand how we need to choose prior to choose a good posterior distribution. And for this thing, we have very helpful distribution called Dirichlet distribution. It's basically very good distribution over simplex with very good density and with very good properties. And the property is that if we have categorical observations and we fix prior from Dirichlet distribution, posterior also will be from Dirichlet distribution. So as here, dir was not loaded, unfortunately. But yeah, if prior from Dirichlet, posterior also will be from Dirichlet, where likelihood is categorical distribution. So, and with this information, we can say, okay, But our samples from transitions are just samples from categorical distribution with a lot of categories. Of course, number of states is particularly large, but it's just some categorical distribution. And we can say, okay, if we fix prior as Dirichlet, we end up with posterior that will be also Dirichlet distribution, and we can somehow more efficiently think about what's going on with this algorithm. And basically, the effects that we see for example, for any posterior sampling thing, that for any distribution, we have two properties: concentration of it, how it's good constraints around mean, median, etc. That typically leads to exploitation is because it's allows us to control the closeness of this estimate. But also to do efficient exploration, we need to understand anti-concentration properties of this distribution. That means that it should be spread it well enough, but not too much. Well enough to have exploration, but not too much to have exploitation. But this very good philosophical things I was talking about, but for a moment, for posterior sampling algorithm, it's for as described here, it's not clear how to provide anti-concentration result. And one possible solution to make it a little bit easier by changing the algorithm itself. So we can try to change analysis, but we can also try to change algorithm. And the way how we will do it, we somehow introduce additional optimism to this algorithm to make it prove kind of more easy, more doable. And that's the point of what will be afterwards. Okay, on this slide, I introduced two algorithms that we was describing in the two papers. So first algorithm, it was bias UCB-VI, extension of bias UCB to RL. And basically, compared to posterior sampling, we replace just one sample from quantile, from one sample from distribution, to take in quantile over the distribution with respect to some large enough quantile level. It's needed to make sure that this Q bar will be upper approximation for optimal Q star. And it could be verified not for all the value function itself, that is very difficult object in terms of our distribution P, but step by step. So we can prove something for one step of this thing, and afterwards, since we have everything with high probability, taking one more union bound will not harm too much. And that's why it's easier to prove. And for this algorithm, yeah, we can show near optimal regret guarantees of this order. That's almost matches minimax lower bound. Alternative way to do it is, okay, for if it's not clear how to do something with one sample, okay, let's just take maximum over some number of samples, and and try to analyze this algorithm. It will be somehow multi-sample type of posterior sampling algorithm. And this algorithm, so the second one, optimistic posterior sampling, is computationally implementable, just as said here. And basically, one of our achievements for all this thing is just it's enough to take some logarithmical number of samples, if not very large constant. So this also can be very important. But in practice, we will use just value 10, something like that, or 8. And it worked. For the left algorithm, it's a little bit easier to analyze than the second one, but it requires to approximate this quantile because this distribution does not allow us to compute quantile in closed form, unfortunately. And we need to calculate it.
Oh, just a quick question. Sorry. So this P V bar is like the push forward of V bar under P, right?
It's
like
was described here. It's expectation basically. Sorry, just described here. It's action of the Markov kernel on the function.
Okay.
Yeah. Thank you very much. Yeah, I forgot to
And I guess when you're talking about sampling like computing the Bayes thing efficiently, you could take a whole bunch of samples, but you'd need about 1 over kappa samples or something, I guess, or 1 over 1 minus kappa, depending on.
Yes.
Yeah.
It's possible to approximate like that. So for this algorithm itself, if you, for example, take a look on the paper that was published, this kappa will be very, very close to 1. So this means that we need enormous number of samples to approximate it. And that's the reason why we also introduce a second algorithm and make it more computationally friendly. So we just for the first algorithm, we was not caring too much about the computation in the tabular case, because all the point will be described on the next slides. I will trivial spoilers. But yes, so this form will be enough to just show that, okay, this principle works very good. And basically, with the technique from the second paper where we introduced optimistic posterior sampling, we've refined inequality. We can take this kappa not very close to 1. That makes it computationally feasible to do also.
I see. Thanks.
But it's a very good question. Thank you very much. Okay, and right now I will go to the point of this Bayes CBVI algorithm. So one of the main points is that basically it's very close to Bayesian bootstrap. So formally it will be not Bayesian bootstrap, but it will be more connected to Dirichlet processes than to just vanilla Bayesian bootstrap. But it's not so important. So I will make a reminder for classical statistical concept. That's bootstrap. We have some data set from some distribution, and our goal is to estimate confidence interval for the data set, but the only thing that we have is this data. We don't have anything else. And how we can do it? We can do, for example, a classical bootstrap. We subsample from this data set some capital B times, for example, some kind of 10,000, 100,000, something like that. And afterwards, for each this resampled batch, it can have repeated elements for this data set. We compute means, so we just compute average. And afterwards, we have capital B estimates of the mean. And we compute quantiles with respect to this large bunch of elements of these B elements. And for example, we want quantile for the 0.9. We need to take element number out of some very large number of elements. It's not exactly maxima, but it should be rather close to maxima if we want to have upper quantile. That makes sense. But there exists also alternative to this procedure, and also there exists enormous number of alternatives connected with the world of multiplicative bootstrap. But one of the examples that we will consider here is Bayesian bootstrap. The difference that we try to subsample not elements itself, but we said, okay, for our estimation of the mean, we have weights 1 over n. But let's just replace this 1 over n to some distribution over simplex with the same mean, and estimate quantile over this thing. So, and basically, what's Bayesian bootstrap doing exactly this thing? So it samples from uniform distribution over simplex, or it is just Dirichlet distribution with n components, the n size of data sets a lot of times, compute new mean estimates for all this weighted estimates without resampling the data, but resampling only with the weights, and compute quantile over the sequence. So it's procedure that was invented a lot of years ago, and in some sense, our algorithm, we try to generalize our algorithm to deep array. It will be very close to Bayesian bootstrap. So what do I mean? Let's introduce some classical things that was going on in deep array. So if we do some DQN type algorithm, we introduce our targets, and afterwards we try to regress with respect to these targets. So for this thing, we have some targets that are just our reward plus value for the next state.
Daniil, can I ask a clarification question?
Yes, of course.
Why is it called Bayesian bootstrap?
Because typically there also exist some prior observations that we have. And that's kind of the idea was that it's it's easy to think about it as an update of this kind of posterior distribution. So basically, it's Bayesian because it's connected to posterior things.
Okay, interesting. I see. In the weight space, you're in a probability simplex, and then the Dirichlet would be the posterior for sort of.
Yes.
Yes.
So I would also say that that was understood it later than this Bayesian bootstrap. I think I'm not sure, but most probably that this Bayesian bootstrap is basically sampling from if we introduce Dirichlet process over our samples. If we say that it was generated from some Dirichlet process, our distribution P. And we try to sample the over the space of distributions. So we have some prior from Dirichlet process, and we have our Dirac distributions, this new one, sampled from this on the distribution space, basically. And we can consider Dirichlet process. I have one small slide in the very end of everything. And basically, Bayesian bootstrap. It's sampling from this posterior. So we're sampling our weights and Dirac measures over all these things. It's the posterior distribution in the space probability measures. So I'm not sure that it will make everything more understandable, but
somewhat. Yeah, thanks.
Okay, yeah, perfect. Okay, let's turn back to implementation itself. So right now, I can just rewrite everything and approximate everything. So let's just first thing that put rewards inside of the quantile, because rewards in our case are fixed. Typically, it can be random, and we also need to approximate it over quantiles. But let's see that everything works here. And we just have, we can, by aggregation property of Dirichlet distribution, that means that in our case, our Dirichlet distribution consists of all integer components. And basically, it can be decomposed in this way. So for this equality. So it's some property of Dirichlet distribution because its density is just polynomial to the power of number of parameters of the Dirichlet distribution. And we can kind of decompose it back to just product of components one by one. So this thing is called aggregation property of Dirichlet distribution. And we can rewrite just pure equality that our upper Q function is quantile over uniform Dirichlet distribution. If this weighted sum of our targets and also prior targets, that, for example, in theory, it requires to be from one fixed artificial state that does not exist in real MDP, but it's somehow artificial, to make sure that we're optimistic enough in the very beginning of the exploration process. But if we sum just this, sum everything here, all this quantile, and afterwards we can approximate this quantile by just sampling from Dirichlet distribution one by one, and we end up something that's very, very close to Bayesian bootstrap. So basically, it's exactly procedures that I described on the right-hand side. And in some sense, our algorithm proves bootstrap validity for such a type of things, such bootstrap validity for this target, for things that appears in array. And in some sense, the validity of our algorithm is the validity of Bayesian bootstrap for this thing. But the next question is, okay, how we can generalize this thing to deep array if we have such approximation? But basically, the very, very important property of Dirichlet distribution, it just is basically normalized exponential distribution. In the case of if we have not uniform one, but 1 over some constant, it will be gamma distribution. But anyway, it's some standard distribution, and moreover, it's normalized version of this distribution. In particular, that means that, okay, our our q-value is quantile over some number of things, for example, 10, because we in deep RL we cannot afford to have 10,000 heads of q-value, at least on small experiments. And we want to estimate this means, this averages with Dirichlet weights. But basically, if we just rewrote this weights is this weights zeta over sum of zeta, we can just say, okay, but this aggregate bar is solution to exactly this regression problem. So we just do least squares, but least squares weighted with exponential random variables. And for each b, it will be our head of our q-value. So we will have several heads as exactly as in Bootstrap DKN. And for each head, we have individual weights that reweights randomly our observations from point of view of regression problem. And afterwards, we can replace X with some neural network, and that's it.
So you probably said it, but like maybe I didn't pay attention. The negative indices mean what?
Excuse
what
me?
are these negative indices? N starts from negative and 0. Like
yeah,
it's
it's
data with some zeros, or like okay, yeah, that's the padding.
Yeah.
So what do you use there?
Yeah, actually, in practice, it turns out that it was not so useful, unfortunately. So here, the theory a little bit different with practice, because this prior targets was not very useful, because it's very hard to tune this value for this artificial state in practice.
Oh, I see. It's from this slide. So
yes.
It's like that is supposed to be some high value or something.
This thing should be supposed to be maximum value in theory, but in practice it will end up with very a lot of instabilities in training of regression.
Okay.
Okay. So right now I will continue and show small experiment of pictures that so this idea actually works. It works good things that it works and works on the level of Bootstrap DKN. That was just generalization of usual posterior sampling in some sense, but it wasn't working not much better. And kind of on the for deep RL we have this slide, this right part of the slide. For the left part of the slide we have this basis ECBVI implemented in tabular setting, and basically we also propose some incremental version of it just to reduce a little bit computations, and it turns out this incremental version also very good in practice, and it's for this environment it's kind of almost matches the posterior sampling. That seems to be very good thing. And here you can see this bad behavior of UCBVI, because the bonuses are over optimistic, and it forces explore algorithm too much because of the shape of these bonuses, because they cannot decrease faster than they can. But for things that related to posterior sampling, it's possible to understand more about the environment, and in some sense, it's also can be observed from theory of it. But for theory, I will more talk about the second algorithm with maxima over posterior samples, because it's in the spirit it's the same proof, very close. Only in the second algorithm we used refined some concentration inequalities that allow us to have efficient version of it. But if you take a look on the second algorithm, that optimistic posterior sampling, I will recall that it is this algorithm, and we take not quantile but just max over some number of q-values. It's harder to control how much number we need in practice, because quantile is something that's maybe assumed to be better controllable, but taking max is also kind of from point of view of theory, it's almost the same things. Actually, we can control this J very good, and we understand what the order is needed of it. And here, for example, we just take capital J equal to 8 in the both experiments, and yeah, we just reproduce the effect that UCBVI does not work very good on these practical scenarios. Posterior sampling works very good, and optimistic posterior sampling works a little bit worse. And basically, it's because of very specific priors that we need in theory. If we use simpler prior, just uniform one, it works better, and it's observable on the second picture, where the major difference it's between, for example, blue and orange curves. It's induced by between optimistic posterior sampling, where we mean optimistic prior, and posterior sampling, where we mean just uniform prior over states, and the most of the difference was about to forget this non-formative prior. So, and right now I will finally move to theory. So typically proof for these algorithms for both by CCBVI and optimistic posterior sampling consists of two parts, and the second part is easy because it's somehow use reduction to known algorithm, and first part is actually the hardest one. So the first thing that we need to show is that uses anti-concentration properties of our algorithm is that, we want to show that algorithm is optimistic. That means that our Q bar is larger than Q star, and V bar is larger than V star. So that's the thing that is needed to simplify analysis a lot. And actually here it's kind of crucial to do it. And for concentration part, for example, we can show that for any parameters, for any letters that you see here, we have such inequality that our posterior multiplied by V bar minus just maximum likelihood estimate of everything is controlled by quantity of this thing. And this thing may resemble just usual Bernstein type bonuses. And actually, that means that our posterior sampling, first thing, that automatically adapts to variance, because in the expression for posterior distribution, we never use any variance, we never use any expressions for V bar. It's just some distribution. It's just Dirichlet distribution over whatever we need. But it turns out that it automatically captures the variance if it's have a product with this V bar. So we compute expectation of the value for the next state for distribution for states distributed from this Dirichlet. We end up with some estimates that will be very variance adaptive. And this allows us to just, in some sense, reduce proof to just usual UCBVI, for example, because we can just upper bound all the estimates of our algorithm by estimates of UCBVI up to some constants that appears under this big O with tilde. So basically, our algorithm is no worse than UCBVI given optimism. Because without optimism, so we can say that it's just smaller because we can take zero bonuses, but we don't have exploration properties. The first part allows us to provide provably exploration, and second part, we just say that, we just don't much worse than UCBVI, but UCBVI is minimax optimal. So that means that we can finish the proof. And also right now, I'm just starting talking about some additional technical details that appears to allow us to have this capital J to be logarithmic one, and it's a lot of tricks. So first trick that, as I a little said before, we need to introduce some prior, but this prior should drive our exploration in the very beginning. So we need to have some sense optimistic prior. But for initial MDP, we don't know anything. So, and we just add our pseudo state by ourselves. So we just introduce some technical pseudostate, and we just put prior to all this pseudostate. It does not exist in the real MDP, but it exists in the computation of Q-values, and we can never move to this as 0 in the real life. But our prior sometimes remembers that, okay, there exists some very, very good states that we cannot reach, unfortunately. It's understandable later, but there exists some very good states as 0. And also there's needed some trick that's called posterior inflation, that we need to a little bit increase variance of our estimates. By dividing parameters by kappa is basically increase variance in kappa times. And all these tricks is needed to prove this bound. And here the main I would say guest of all this thing that allow us to prove such type of inequality without any additional constraints, without additional switching between phases, and with small number of samples is very, very tight characterization of Dirichlet weighted sums. So we have some parameters with additional shift +1 that I will describe why it's needed a little bit later. And we have some distribution from simplex, so just average over these alphas without this +1, without taking account this +1. Alpha bar is sum for all alphas. It's not average, but just sum here. Yeah, and let's take alpha 0 large enough. That means that it should scale with this epsilon. That I will introduce later. So if epsilon equal to 0, alpha 0 equal to infinity, we cannot afford it, but it somehow scales with it. And additional logarithmic 1. Logarithmic dependence can be avoided by introducing some conditions on the smallest weight, alpha m, weight that corresponds to smallest atom by value function. So we additionally have some technical assumption on alpha 0, and we also need to have separation between the maximum value, that is f0, and all other f by at least 2 times. So we need to have a very, very large weight that will be large enough. And that makes sense if we try to prove something like anti-concentration. If we want to make sure that the probability that we larger than something is large enough, we need to be sure that it will be in case if we have this alpha bar small enough. And to do it, we need to this optimistic prior. And basically the main thing that this probability looks like some scale factor at just arbitrary close to 1 if we take epsilon large enough. And this thing that is not so easy to read, but it's easier to read, the version on the bottom. We have our probability is controlled by some polynomial of 1 over alpha bar and exponent of alpha bar and some projected Kullback-Leibler divergence. And basically, that is equal to this k-inf that have dual form with this maximization over lambdas. And basically, this thing, all these things implies that we actually establish some inverse Sanov type bounds, but in a non-asymptotic version of it. So the first thing that I will show how to actually use this inequality to prove optimism. Why we need just logarithmic number of samples. Basically, first step, we will show that this max larger than the pH V star. So we have the same V star for the both sides of the inequality. And we need to show that this thing holds with large probability for all possible parameters, S, A, H, T, etc. So basically, the idea is the following. We need to show the only thing, that the probability of surpassing this pH V star is lower bounded by some constant. Just some value 0.01, 0.0001, something rather small but constant that will not depend on anything, on number of states, number of actions, and most importantly on time, on the horizon. And basically it's enough to do it, because in this case we can just arbitrarily control probability by taking max, because we have such a nice inequality to control this thing, because max will be smaller only if all the guys will be smaller. And afterwards, we apply our inequality with some arbitrary epsilon, for example, 1/2, and we end up with something like that. So something that scales between this projected Kullback-Leiber multiplied by some factor dependent on n over our kappa that allows to control the variance additionally. But it turns out that this k-inf constrains very well. That means that n bar multiplied by k-inf is of logarithmic order, and we can just take kappa to control this thing to just kill both terms. And for the second part, I will almost skip it. If we have these things for V star, afterwards we can just do usual induction. Just we can say, okay, well, Q bar minus Q star, it just tilde V bar, lower bound V bar with V star, and end up with optimism.
Can we go back just for a second to the previous slide, last display location? That was a little bit like fast, this concentration of k-inf. You said that k-inf is concentrating fast.
Yeah, so it's basically some Kullback-Leiber divergence. So Kullback-Leiber itself.
What's random there?
Random there is that we have here n bar. So our Q bar consists of this Q here. It just almost p hat, but with additional prior.
Wait, so what's random in that expression Q?
This Q itself.
Okay, what is Q?
Q is almost p hat.
Almost what?
Yeah, we have p hat, yeah. So let me just.
P hat?
Yes, yeah. So it's a lot of p's.
Which one?
Yeah. So here we have. So we have p hat. Yeah, it's just a maximum likelihood estimate of our model, but it's random itself because because it was introduced by samples from our model, and with respect to the samples from our model pH, we compute everything. We compute this concentration. P hat, so it's random itself.
Can you go to the slide where that you have Q?
Yes. This Q is shifted version of P bar. P bar is P hat with prior, and shifted because I removed this +1. Yeah, so it's a little bit complicated.
What is +1? Oh, that's
this one.
Okay.
Yes, I need to remove it because of technical thing. Maybe I will not have time.
Okay, so let's start at this inequality here. Like here we have P bar in the argument of k-inf. Okay, like that's what p bar is that? That's p bar of
yeah, it's okay. I understand confusion, right? And I was not thinking about that. It's confusion before. This p bar here, it's q here, basically.
Yeah. Okay. Right, and then the weights are the alpha is going to be random.
And this weights can be random because it was samples from categorical distribution from our pH.
Okay.
And this thing alpha itself random in our case. That makes everything even more complicated.
Yeah, I wonder about the dependencies. I guess I'm not tracking it. Like what is sampled from what after what, and like can you condition on what you need to condition on? And
here I have these counters. Okay, it should be SA and go to S prime. I condition on this thing, and I have this inequality. But this zeta here depends on n bar. N bar is random. Bar is a number of its counter up to with additional prior.
And P bar depends on N bar?
And P bar is a normalized version of N bar.
Yeah.
P bar here. Yeah, and here this Q, okay, yeah, I understand this here, this confusion because this Q is P bar in terms of this theorem. Yeah. It's a little bit shifted version of it.
Got it.
Up to this +1. Okay, and yeah, and this thing, yeah, actually, yeah. So since this Kullback library between something like p hat, very close to p hat, not actually p hat because of prior, but prior is small. It's this thing can be upper bounded, this k-inf, as by Kullback between p hat and p. P hat is our sample distribution from p, and this p. And this thing, Kullback itself, concentrates with order 1/n.
I see.
But here we also need to take into account this k-inf can be concentrated much better, because usual concentration with Kullback is cannot be dimension independent, unfortunately. But this thing can. And this k-inf constrains dimension independence. This is really logarithmic factors without any dimension here. It's under logarithms. Okay, I mean, I'm a little bit here. Yes, under logarithms there can be some dimension. Maybe I don't remember, to be honest. Yeah, it's, but it's basically does not depend linearly on dimension.
Okay.
Okay. Okay. Thank you for the question.
So sorry, what is the dimension here now? Is it the number of samples or
Number of states.
number of states?
That's yeah. Make everything yeah. Because our pH is a distribution of the states.
Right.
Okay. Yeah, and yeah, let's continue with this. Yeah, with this classical argument. It's yeah, all the optimistic Rayleigh algorithms, as what I know, proved in this way. We just use induction, starting from capital H +1, where everything is 0, and afterwards we just replace V bar with V star. And for V star, since it's fixed a priori, we have concentration properties. Everything works. So, and right now, yeah, unfortunately, I don't really have time to a little bit discuss how to prove it. So, if I will have time, on the discussion, we can talk about it. But yeah, but basically, I have just several minutes. Yeah, let's just sum up a little bit what was done. So the main, I would say, idea of what was going on. So we have posterior sampling algorithm that's very good practically, but it's very hard to prove something for it. And we have optimism that have very good machinery to prove it for it. It's very well developed. A lot of papers exist on optimistic algorithms. They're very, very user-friendly. I would call it like that. But they more complicated from practical perspective. So, but okay, we can merge it. We can just make some optimistic posterior sampling algorithm in different types. We can take quantiles, we can take max, we can take anything that depends only on pH itself, and end up with algorithms that will be at the same time minimax optimal, because typically good quantities of Dirichlet distribution just knows about variance in some sense. And that's that's more or less enough. And also because of optimism, somehow we can, in some sense, reduce everything to known optimistic algorithms. If we do it good enough, if we take a good function, for example, maxima of a small number of samples, we also end up with computationally efficient algorithm. And with this Bayesian bootstrap trick, we can generalize all this zoo of algorithms to deeper resetting. But yeah, so one thing that's very interesting for me itself is that very interesting problems that appears in the analysis of this algorithm, as what appears with this Dirichlet weighted sums. And it's very interesting to understand how we can prove something for just usual posterior sampling algorithm. Just we want sample from Dirichlet distribution and nothing else without any maximum. Okay, I think that yes, some things like posterior inflation will be needed for proving it, because the variance of Dirichlet distribution itself is small. So I think it will not allow to prove it. But yeah, with some additional increasing of variance by this trick, division over kappa should be enough to have some guarantees, but right now it's not clear how to prove something for it, because it will be much more complicated, because in this case we need to have anti-constraction result not for just Dirichlet and product of Dirichlet vector with some fixed vector, but we have some sums of this thing. And we need to understand how this thing acts from below. Sorry, here should be a lower bound. How this thing acts from below. Because, okay, from above, we can understand behavior of the exponential moment of one element of the sum, apply Markov inequality, everything independent, everything easy. But for anti-constration, and if we don't want to have some exponential dependence in this gamma as I described here, for example, if we don't want to have it exponentially small, we need to be more trickier. We need to more involved analysis. And the first steps to do it, it's somehow some simplify the results, because the method that was used to prove it actually was historically was not well suited for non-asymptotic analysis that we definitely need for all the story of this exploration in array. And I think I'm out of time. So thank you very much for your attention. If any question?
Yeah, thank you. You're very much on time. Thank you.
Hello. Thank you. I have a question about. So why do you? So in any intuition, why do you select like that Dirichlet prior for the transition kernel, and also n bar inside the prior? So do you have any like intuition behind?
So can you please repeat the question? Sorry.
Yeah. So I was about the Dirichlet prior on the transition kernel. So why do you use that, and why do you use that n bar?
So this basically question about prior. It's very good question. It appears from this result. It appears technically inside the proof. Unfortunately, a lot of strange conditions here appears inside of the proof of this thing. So if we take a look on this condition, so for this theorem, we have, okay, we need to have alpha 0 large enough. And the function itself, it's our value function. In our case, f0, it's the value function for s0, for our zero state in some ordering. Okay? It should be equal to some b0, some large number, and all other values should be at least 2 times smaller than this b0. And that's the reason why some strange prior appears. And this n bar, it's basically just n, but taking into account this prior samples to this s0. Just the same thing as n, but for initial for state s0 that does not exist in MDP, we put weight of this order, of this constant plus logarithm of number of visits. Okay, hope I answered your question.
I still didn't see the prior in this theorem. Okay. Okay, somewhere. Okay, thank you.
In this theorem, there is no itself prior. So in strict sense, because this theorem does not take you tell you anything about Bayesian inference, just pure probabilistic result. But we can interpret that, okay, we need to have alpha 0 large enough, and value function for this 0 state should be also large enough, and larger than it's possible to do with any normal state. We can take, for example, very large uniform prior, but even this thing will be not enough, because we need at least 2 times separation between B and B0. B is the maximum for all non-zero states.
Okay. Okay. Thank you.
Okay. Okay. Anyone else? Yes, sorry, I cannot see the chat.
Can I ask a few questions?
Sure, go ahead.
Yeah, let's go back to the algorithm side. I think it's in the previous, in the way you extend your algorithm to deep RL.
Extension to deeper. Sorry, can you repeat the question, please?
Yes. Maybe this page. Yes.
Yeah.
So I think this is I think previously in Osman's work in this bootstrap DQ, and the Z here maybe is a Benoni distribution, or that is but they had a Benoni mask. Here you are using the exponential mask, and also another thing that is relevant here is that for every new data set, you can only if in your incremental version you had this Z and B, you sample multiple B for one particular X and also this YN. You're doing incremental sampling, right?
Yeah. Yes.
Yes, I think this and this version. Do you have any guarantee on that version right now, or?
On the incremental version, yeah, I think so. With such an optimistic version, yeah, it's possible to prove some guarantees. At least I remember that it's very connected to the next talk, I would say. Yeah. So basically, for incremental versions that we don't resample these exponential weights, it's also possible to prove the same guarantees. It's not I would say written in the original paper, but I remember that it's possible. So I did some kind of drafts computations. I remember it's possible.
Yeah, I think this is quite interesting. Yeah, that's the first question, and also for that, I think you mentioned that in the end that if we only has one sample, the original version of a posterior sampling RL, I think the Bayesian regret of this the vanilla PSR are still not tight in terms of the lower bound. So is there any result in the current literature that's for Bayesian regret bound on PSR that matches some kind of lower bound? I don't see that result actually.
Okay, that's interesting because to be honest, I was not following too much story about optimization of Bayesian regret for Paris-Saclay.
Yes, even in Bayesian regret in the tablet case, I think there's just currently no result matching to lower bound. So maybe your technique can give rise to some solution, at least for the Bayesian version, because you don't need to prove the anti-concentration if you want to just get into this Bayesian regret bound.
Yeah, sounds very interesting. Thank you.
Yes. Yeah, I think that's my questions and comments. Yeah, thank you.
If you have another question,
hello. I have a question about the optimistic posterior sampling. So the developed the Dirichlet anti-concentration bound gives you some kind of weak optimism guarantee, right? Because the lower bound is a constant. And then by drawing multiple posterior samples, I mean Dirichlet posterior samples, and then this kind of weak optimism guarantee can be boosted to a high probability guarantee, right? And then the regret is like use the optimistic learning algorithm to do the regret decomposition, right?
Yeah, absolutely.
So is it possible to only draw one posterior sample? I mean, Dirichlet posterior sample. Is it possible to do that? You need to have some like a very nice anti-concentration bound of the I think we need to have something like the distribution for the weighted Dirichlet random variables, right? The concentration for that.
Exactly. So yeah.
Yeah, so I'm wondering, yeah, I was also working on it when I was a postdoc in AMI, but I found it is very, very hard to have good. Yeah, so yeah, and also I'm thinking that I think I can't remember the detailed page. I mean, the one you put something like basically you the lower bound part you use a Gaussian, right?
It's
the lower
kind
bound
of Gaussian.
Yeah, you connect with the anti-concentration bound of the Dirichlet random variable to a Gaussian. Right?
Yeah, but almost. Yeah. But important thing that here we have also this Kane thing under this Gaussian. So it's not the classical Gaussian comparison as in kind of classical statistics appears, and we just say, okay, this random variable is almost Gaussian. By central limit theorem, we can approximate it. It's Gaussian, but this Gaussian is needed more or less to understand why this polynomial 1 over alpha is not harmless. I would call it like that.
So I was wondering whether in the left-hand side we can use something like the first order stochastic dominance, and the right-hand side maybe we can use some kind of, so basically the KL part is not nice, but we can use some like the reverse p-square equality to make it depend on something 1 divided by delta square. And then, yeah, because the multiple independent Gaussian is still Gaussian, right? So maybe the left hand might, whether we can have some, basically, yeah, I was thinking whether the right hand side can be made something into one single Gaussian, and then we can use the Gaussian anti-concentration bound to have a constant. Yeah, but I couldn't make it. Okay, this is my question.
Yeah. Thank you very much for your comments. It's very interesting. Yeah, actually, I tried to make some preliminary computation for weighted sum, and I end up with some quantity, not exactly Kane, but something that's very close, that appears in problem-dependent lower bounds for MDPs. So it's something a little bit resembles it, not exactly this thing, but something kind of close in spirit to things that appears in the lower bounds actually for MDPs. This thing is lower bound for bandits. Yeah, so this in bandits we have problem-dependent lower bound that's described in terms of K-inf. If we have weighted sum of it, it's kind of maybe natural to expect something that will deal with lower bounds for MDPs, but it's very hand-wavy intuition. But, yeah. Thank you very much for your question. Yeah.
Okay, there was also one question in the chat. If you could just comment on the advantage of posterior sampling over bonus encouraged exploration. So C is asking.
Yeah. So it's questions that's answered by picture, as sometimes happen. Okay, maybe here it's a bit more illustrative because this environment is a little bit harder. So here we have so just basically plots here. Take a look on the plots. So that's for UCBVI with things that close to what we need in theory. Its is much worse because we have a large warm-up thing with a lot of unnecessary exploration. And for posterior sampling type algorithms, it's better because it's automatically adapts to variance and automatically adapts even for higher moments. So for bonuses to be adaptive to higher moments, for example, we need to just introduce these higher moments in bonuses, and it will be always overly optimistic because we just derive everything from concentration inequalities. For posterior sampling, in some sense, it automatically adapts to variance and to higher moments because it uses concentration Kullback-Leiber, and Kullback controls all the moments. I would comment like that. I hope it's it's helped to understand. Okay, any other questions?
Yes, I just want you to add some comments that I think this is very interesting and work. And I think this, for example, for this randomized exploration schemes, I think the main advantage of this kind of methods is that they might be easily to generalize to deep RL. And one key issue is I just mentioned this kind of incremental update with bounded per step computation. I think that's essentially in your inquiry base USVUI, this type version, right? And also this ensemble things. It's quite similar to this ensemble sampling because right. This ensemble way to do this kind of incremental version. So I think essentially the proof may be quite different because the dependence in this way that your artificially generated noise is dependence in the history. It's not that in every episode you are doing resampling. So I think this proof may be not essentially the same, right? I think this may be some critical difference here, right?
Yeah, I would say, yeah, I can comment something about difference between proof on incremental version and non-incremental. And basically, kind of the hardest part, it's proving optimism. And for optimism, so the main problem with incremental versions is that our basically VT will depend on Pytute, basically. So our model will be depend on the previous values and the new ones. Right. And for optimism, it's does not need it because we proven optimism in the known direction of the star. This makes everything much easier. But for constellation result, maybe it will be different. Yeah, I don't remember, to be honest. I was doing it.
Yeah, because I had some experience doing the incremental version in the linear Gaussian case. Mm-hmm. Yeah, I think this. I see the difficulty there, right? Yes. Yeah. And also, I think I think I want to discuss a little bit with you, if the time permitted. What's the essential benefits using this kind of? This is mimicking beta Bernoulli or Dirichlet multimodal updates, and the other way is you can use like linear Gaussian. When my model is misspecified, I think, for example, the environment is essentially a beta Bernoulli. You can still use a linear Gaussian algorithm to solve this beta Bernoulli environments. But in the converse, do we have guarantee that we can use beta Bernoulli algorithm or some similar way you do to solve like if the environment is linear Gaussian? So I think that's another interesting question for the generality of this kind of, if you want to use a simple algorithm to solve a complex environment, I think that's also another motivation of randomized exploration, right?
Yeah, I think so. Yeah, so that's and actually I think that so it's actually again connected to this automatic variance adaptivity, as it appears exactly on the slide. Because we can just it's more like one simple method that automatically adapts to some properties of the environment.
So, right. That's for example, if you in the linear Gaussian algorithm, you can probably solve a beta Bernoulli environment. There's some literature supporting that. Right.
Mm-hmm. And you can just use kind of more general prior information of whatever you have, and just solving with Gaussian. Okay.
Okay, that's just comments, and it's an interesting question.
Yeah.
Thank you. Right.
Thank you too.